In this tutorial, you will learn how to model a planetary gear mechanism in Blender. A simple planetary gear system consists of three components. The gear in the center is called the sun gear. The outer gear with the teeth pointing inwards is called the ring gear. The three gears rotating around the sun gear are called planet gears, and the platform on which the planet gears are mounted is called carrier. Any of these three components can be made stationary, while the other two have an input and output shafts connected to them. In this tutorial, we will assume that the outer ring is stationary, the input shaft is connected to the sun gear, and output shaft to the carrier. Let's denote the number of teeth in the sun as S, the number of teeth in the ring as R, and the number of teeth in the planet gears as P. The three numbers must satisfy the following equation: R equals S plus 2 times P. In our example, R is 60, S is 12, and P is 24. The gear ratio of a planetary mechanism in our configuration is calculated as 1 plus R divided by S. In our example, the gear ratio is 1 to 6. Multiple planetary mechanisms can be stacked to form a compound drive. This produces a very high overall gear ratio. In this tutorial, we will be designing the planetary gear system shown here by first designing the ring and planet gears, and then the sun gear separately. We have developed an online calculator that generates tooth profile equations and other parameters for a meshing external and internal gear pair. This calculator can be found at www.vinted.com/internal.html. In addition to entering the number of teeth in module, we will also be entering the profile shift coefficient, a parameter we did not use in our previous tutorials. When a gear has 12 teeth or fewer, the gaps between its teeth are not deep enough to accommodate the teeth of the other gear. Here, the overlaps are marked with red arrows. To fix this problem, a positive correction to the smaller gear's profile needs to be applied. The parameter controlling this correction is called profile shift coefficient and denoted by the letter X. As a result, the smaller gear's teeth become sharper, and the gear itself is moved farther away from the other gear. We will be applying the profile shift coefficient of 0.5 to the ring and sun gears, while leaving the planet gears with no profile shift. Let's start modeling. Delete the default cube by pressing X. On the numeric keypad, press 7 for the top view, and 5 for the orthographic mode. Select 3D cursor for the pivot center. Go to User Preferences. On the Add-ons tab, make sure Add Mesh, Extra Objects is checked. Go to the online internal-external calculator at www.vinted.com/internal.html. Enter 24 for external and 60 for internal number of teeth. Enter 0.5 for the internal profile shift. Press Calculate. Back in Blender, add a new XYZ Math surface object by pressing Shift-A, then Mesh, then Math function, then XYZ Math surface. Copy the X and Y equations from the online calculator's external gear tooth profile boxes. Enter 0 for the Z equation. U-min should be 0 and U-max should be 1. Enter 10 for U-step and uncheck the U-wrap box. The V parameter is not used, so enter 0 for V-min and V-max, and 1 for V-step. Press Tab to enter the edit mode, and press Remove Doubles from the Tools panel. Create a mirror reflection of the curve relative to the x-axis by pressing Shift-D to duplicate, then S for scale, then Y, then -1, then enter. In the online calculator, copy the tooth thickness at base number from the left side of the table into the clipboard. Back in Blender, rotate the curve by pressing R to rotate, then Z, then Ctrl V to use the clipboard value as the rotation angle, then enter. Select these two vertices and press F to form a tooth tip. Press AA to select everything. Press Shift D to duplicate, then R to rotate, then Z, then 15, then enter. 15 degrees is the angle between two adjacent teeth in this gear. It is calculated as 360 divided by the number of teeth. Select these two vertices, then press Shift S, then cursor to selected. Unselect the top vertex and press the spin button on the Tools panel. Enter 16 for steps, and 180 for angle. Press AA to select everything, then press Remove Doubles. Press Shift C to return the 3D cursor to the default position. Press Shift D to duplicate, then R to rotate, then Z, then 15, then enter. Repeat with the rotation angles of 30, 60, 120, and so on until the entire outline is completed. Select everything and press Remove Doubles. From the information window at the top, note the number of vertices in our object, 888. Add a circle by pressing Shift A, then Circle. Add 888 for vertices, and 10 for radius. Press AA to select everything, then press W and select Bridge Edge Loops. Press C to extrude, then Z, then 10, then enter. Select everything and press Ctrl N to fix normals. Press Tab to exit the edit mode. Our planet gear is ready. Call it Planet. For the ring gear, add a new XYZ math surface object. This time, copy the X and Y equations from the online calculator's internal gear tooth profile boxes. All other parameters are the same as before. Enter the edit mode by pressing Tab. Press Remove Doubles. Duplicate and create a mirror reflection. In the online calculator, copy the tooth thickness at base number from the right side of the table into the clipboard. Back in Blender, rotate around the Z-axis by this angle by pressing R, then Z, then Ctrl V. Connect the two rightmost vertices by selecting them and pressing F. Select everything, duplicate and rotate around the Z-axis by 6 degrees, which is 360 divided by the number of teeth in the ring gear. This time, do not use the spin tool to connect the two adjacent teeth. Just connect them with an edge by pressing F. Select, duplicate and rotate by 6, 12, 24 degrees, and so on until the entire outline is completed. Select everything and press Remove Doubles. According to the information window, this object has 1320 vertices. Press Shift A, and select Circle. Enter 1320 for vertices. Scale it up until it fully encloses the tooth outline. Select everything, press W and select Bridge Edge Loops. Press C to extrude, then Z, then 10, then enter. Select everything and press Ctrl N to fix the normals. Press Tab to exit the edit mode. Our ring gear is finished. Call it ring.